It talks? Oh my God, is that a new thing? Okay, welcome to review session number 3. So our plan is to run through questions 21 through 50 from our review set. I would advise pulling out a notebook so you can work along with us. I'll show the problem on the screen. It's also was attached to the email that I sent. Here we go. Okay. Problem 21, as a general rule, I'm gonna go through the problem, give you 30 seconds to a minute to start figuring it out, and then asks you to share out any ideas. So a block slides down a hill at a constant speed. Which of the following describes the mechanical energy of just the block and the mechanical energy of the block Earth system? So first, the mechanical energy of just the block, and then of the block Earth system. So this one's an energy and systems question. All right, who thinks they might have an idea, or who can at least talk me through one element of it? Let's go piece by piece. Go ahead, Zagani.
I guess you can start off with the energy of the block, because theoretically, if it's going down a hill, then it's starting with some potential, and then by the end, it should be, starting with some potential, and throughout, it's getting converted to kinetic.
Good.
So in theory, it should be like constant, but it never stipulates that it is frictionless. So I would assume that it would decrease.
Okay, so it does indicate that it's going to go down with a constant speed. So we know that it is not frictionless. There would be friction. However, friction is not part of mechanical energy. Remember, mechanical energy is just going to be potential energy and kinetic energy. So we can ignore thermal or friction. So let's look at just the block. Just the block does not include the Earth. If it doesn't include the Earth, we are ignoring potential energy. So this one would just be kinetic. The block Earth system, now that the Earth is in it, it could have potential energy and kinetic energy.
Wait, so you can't so in order for it to have potential, does it basically just need that frame of reference of Earth?
Yes.
Okay.
Yes. Anytime they're talking about systems, if they include Earth in the system, you can include potential energy. If they don't include Earth in the system, no potential energy. Okay. So that would mean just the kinetic energy. Does the kinetic energy change if a block is moving at a constant speed?
No.
No, because kinetic energy is 1/2 mv squared. Speed is constant, v. Mass of the block is constant, m. So this one must be stays constant. I'm either A or B. Then it's either going to stay constant or decrease. I know my kinetic energy is going to stay constant, so I could box that one. That guy will stay constant. What happens to my potential energy if I'm going down a hill?
It's going to decrease.
That's right, Jordan. That would decrease. So I would see a decrease of potential energy and a constant kinetic energy, and added together, those would end up with a decrease of kinetic energy, or sorry, of total mechanical energy. A decrease of total mechanical. So that would leave me with B. Yeah. All right. Let's try the next one. Question 22. Question 22 has a graph, a line graph showing force versus position, force versus distance. A force meter is used to pull a block of unknown mass on a frictionless table. attached to a spring fixed to a wall, and the reading is plotted against the position of the force meter. Okay, so basically position in centimeters would be X, because this is on a spring scale. The spring force would be F, and I know that it has a spring constant, so K is somehow involved. Which of the following could be determined? Choose 2 correct answers. Look through your options, see which ones you feel like may be correct. All right, give me 1 correct answer. Sorry, we need more reading time.
A.
A. Alex, why do you think A is correct? You are right.
Because the equation for it needs the force, the displacement, and the spring constant. You already have the force and the displacement, so you can use that to determine the spring constant.
Excellent. So that could be listed as F equals KX, or on your physics everything sheet. I don't know if that's the one that they use. Do they use K equals? I'm looking on the physics everything sheet to see if there's an F equals KX or a K equals F over X. Yeah, it is F sub S equals KX. It's towards the bottom, F equals KX. Okay, so that's correct. A is 1 right answer. What's the other one?
C.
It is C. Why do you think it's C?
Well, I heard of this interesting tip once about taking an AP physics exam. When it gives you a graph, you can either look at the slope or the area under the curve.
Uh-huh.
So for this one, I tried finding slope, and it would be like Newton over like centimeters, so like Newton meters, I guess, or something like that. And I don't even know how I would apply that to this.
That's
the
K.
area, yeah, and
That's a spring's constant.
enough. But then like the area under the curve is essentially just force times distance,
Uh-huh.
which is so yeah, that's what I thought.
Yeah, and force times distance is work. Yep. So those are the 2 things you can solve. You could also do some process of elimination if you want. The acceleration of the block at a given position. Well, to find acceleration, I would need force equals mass times acceleration, but it's an unknown mass. So I don't have that, so I can't find the acceleration. I have a force, but no mass. And then for part D, the distance the spring will stretch if hung vertically, that is also dependent on the mass. It'll stretch further if I hang a larger mass on it. So again, I need the mass. Okay. And Izagani is correct. The 2 things we can find are the slope or the area under the curve. And in this case, the slope is the spring constant and the area under the curve is the work. You could also say work is equal to change of energy. And I know that I can find the energy because energy is 1/2 kx squared. Cool. All righty. Next up, let's do some springs. 2 carts are compressed in the same distance, d, against identical springs and released from rest. They separate from the springs and collide and stick together. In which direction will the 2 carts move after the collision? So they're both going to get pushed the same distance back, that part. That I'll call x and x. And then they both take off, leaving the springs, moving towards each other. And the question is, after they collide, which way do they go? Welcome, Jenna. Good to see you. Okay, so I find this one very tricky. Who has a starting point? How would you start to attack this one?
Well, since the springs are identical, they should have the same stored spring potential energy
Good.
since they're compressed by the same distance,
Okay.
which means that kinetic energy should also be equal.
Good.
The heavier one's going to be slower.
The heavier one is going to be slower. Okay.
hmm
So I'm going to call this one 1 and this one 2. So I know that V2 is going to be less than V1.
hmm
Okay.
Now that you have the velocities, could you almost turn this into like a momentum problem?
Yes, you can. So
It has to be conserved between the two. So you can kind of just like cross compare the initial momentums from both and then see from there where it should end up afterwards. Like, I don't know if that makes any sense, but
yeah, you're right. Yep.
that's kind of basic inclination.
Whichever one has more momentum at the beginning, it will end up winning and pushing in that direction afterwards. So which one has more momentum at the beginning? Now here's where this one gets tricky. We have to know how much bigger V2 is than V1. So Alex got us started on the right foot. We do know that the the spring potential energies, why did I use K? Use of S, sorry. Spring potential energies have to be equal. So the kinetic energy is going to be equal. So that means for part 1, 1/2 mv squared is going to be equal to 1/2 mv squared, V1 and V2, right? They both come from the same spring constant and they both go back the same distance. So they both have the same spring potential energy, which means they both have the same kinetic energy. But I know that 2 has 2m as its mass instead of 1m. There's 2 masses. I can cancel the 1/2, 1/2. I can cancel m and m from both sides. So V1, to get it by itself, I got to take a square root. So that leaves me with V1 is equal to the square root of 2 times V2. So V1 is bigger than V2, as you mentioned, and it's bigger by a rate of square root of 2, or if you're more of a decimal person, 1.41 V2. Okay. Now I can do my momentum piece. So the winner is going to be the one with the most momentum. because when they collide and stick together, that one is going to have more momentum coming in and it'll push in that direction. So for momentum, now I'm doing the momentum of one. So this side is the one side and this side is the two side. The momentum for part one would be m times square root of 2 v, right? Because I put in v1, m1, v1, or that would be root 2v, versus 2m times v2. Which one's going to be bigger, square root of 2 or 2? 2 is bigger than square root of 2. So 2 is our winner. This side would push more with the momentum, so it should move to the left. So that leaves me with left as my answer. I believe there may be another way. I think that the teacher who posted this one had a different solution, a different way of solving this one. But for me, I go through an order of operations for AP questions generally. Can I solve it through energy? Then can I solve it through momentum? Then can I solve it with forces? That's generally the order in which the AP prioritizes things. Energy first, momentum second, forces third. So if I'm up in the air about them, try energy first. In this case, it's using both of the first two, energy and then momentum. All right. Problem 24 looks very similar, but a slightly different question. Two carts are compressed the same distance, d, against identical springs with spring constant k and released from rest. They separate and collide and stick together. Which spring does more work on the cart that pushes it? Which spring does
Does it-
more? Go ahead.
Wouldn't it kind of depend on, I guess, what you define as a positive and a negative direction for this?
It could. It could. So, what do you think that's based off of?
Well, I mean, because first what I was thinking is that since work is equal to force times distance, and they're both compressed the same distance,
Okay.
and as has been stipulated before, they have the same spring constant because they're the same spring.
Yep.
So I would assume that in theory, like if you just line them up right next to each other, they would be exerting the same amount of work. But since one is going to the left and one's going to the right, then you have a negative and a positive. So I guess you have to kind of delineate there, but I don't even know if that's necessary, or is it?
It is not. For,
Okay.
energy, we don't have to worry about negatives and positives.
Okay.
Okay. So based off of that, you've got F delta X, or F times distance, which would be equal to the force times the distance on this side. Okay. And they should both have the same work done, because work equals work. We could also say work is the change of energy. As Alex mentioned last problem, where is our energy coming from?
The spring.
Spring potential, right? And his starting point was that the spring potential energy in the first one is equal to the spring potential energy in the second one. That's our change of energy. How much work is being done? The work is being done by the spring. So it's the spring potential energy. Or I could write that out as 1/2 kx squared equals 1/2 kx squared. By having the squareds in there, it makes it more obvious that I'm ignoring the sign, whether it's positive or negative, because the squared will take away the positives and the negatives, or it'll turn them both positive. So that would leave us with D. They do the same amount of work, a positive amount. So there is a value of work there. You could do force times distance, or you could do 1/2 kx squared equals 1/2 kx squared, or spring potential energy equals spring potential energy. Those are positive values. Okay. All right. So those were a bunch of spring energy questions. Questions anywhere there before we do a little momentum piece? Because I shouldn't spoil the lead. Okay, on to number 25 then. 25, a clay ball is shot and sticks to a sidewall inside of a cart that is free to roll on a floor. In which direction is the cart moving just after being shot and just after the collision with the wall? Okay. So just after being shot would be the ball is in the air here, right? But it has not yet hit the wall, and the ball is moving that way after the ball has collided with the wall. And we're looking at the cart's direction. Okay, so let's start with the cart's direction just after the shot. Which way is the cart moving just after the shot, and how do you know?
It would be leftward, right?
It would be leftward. How do you know?
Because for every action, there's an opposite and equal reaction.
Good. Since the ball is moving to the right, the cart has to be moving to the left. Now, I would imagine the cart is moving to the left much more slowly because the ball is probably much less massive. But the cart has to move to the left. Anybody have another way of determining that the cart might be moving left? A test-taking tip.
Wow.
Just the overwhelming amount of leftward options.
Yeah. I mean, just as a general test-taking tip, they give you leftward, 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 and then the cart's direction of motion after the stick is right, left, none, or none, right, right? It's probably one of these leftward ones because there's 3 lefts and 1 no motion. There's no like to the rights. So it's probably left. And you're correct. It is left based off of equal and opposite forces. Okay, what about right after the stick? After the ball re-collides with the cart, then which way are things moving? Or just which way is the cart moving? Right, left, or not at all?
I'm probably wrong, but since the motion, since it's the equal and opposite force, wouldn't it be no motion since the force is being applied like in the opposite, the same force is being applied in the opposite direction?
That is correct. So we started the cart moving left because the ball went to the right. Then the ball hit over here, which pushes the cart back in the way that it was going previously. So it brings it back to a standstill. So it's basically like I push something this way. Let's say I push something this way, and then it hits again and it stops it. So it would be leftward and then no motion, because after the ball and the cart collide, it's like it was before the ball was shot. Everything is back in the same static situations. It'd be the same static starting point. All righty. 26. Cart 1 and 2 move towards each other at speeds of 3 and 4 meters per second, respectively, as shown above. They stick together during the collision. Which of the following is true about the collision? And you got 4 options. As a time saving tip, you only have to find one true one in this one. So anytime I get to one and I'm like, oh, that would require calculating, I just move to the next one and see if that one just happens to be true. Right? So I would read all 4 of them, see if one of them is true without having to calculate anything, and then go back and recalculate if I have to. Okay, which one is the true one?
I'm not sure exactly which is the true one because I don't know if I'm just remembering something incorrectly.
Mhm.
But like as a preface, I think it's a pretty key point that it says like right in the middle that they stick together during the collision.
Good.
So, and after you mentioned if something is true or not, I just kind of looked at C because it's an inelastic collision. And I feel like I remember something having to do with kinetic energy being mentioned in terms of inelastic collisions. But maybe that's the wrong one, but
You're correct.
At least
There
that's
is something to do with kinetic energy and elastic or inelastic collisions. Kinetic energy is conserved in elastic collisions, but not in inelastic collisions.
well, I guess
So-
that's a good way to get rid of an option.
There you go. We can now get rid of C because it is not conserved in inelastic collisions. All right, so I would go, let's see, I would go with B. And the reason that I would go with B is when they collide, they're going to be touching each other. Alex Lazada, what does every force have?
An equal and opposite reaction.
Equal and opposite force, right? So since they're touching each other, this force has to be equal to that force, right? Every force has an equal and opposite force. Impulse, what's the equation for impulse? Maggie, I think you got it.
Well,
Force
impulse and
average times-
momentum are the same thing.
Impulse is equal to momentum. And Alex?
Force average times the change in time.
Cool. So it's the force times the time.
Yes.
In this case, it would be the time of impact, right? The time that they're actually contacting each other. Would they also have to be touching each other for the same amount of time?
Yes.
They
Yes.
collide. They collide and stick, right? I can't have one hand touch the other hand for longer than the other hand touches the first hand. They're both touching each other. It's the old sibling, stop touching me. You stop touching me. You're both touching each other. You can't be touching something without it touching you back. What? So I know that the forces are the same. I know that the time is the same. So the impulse has to be the same because impulse is equal to force times time. Impulse on your physics everything sheet is listed as delta P. I use J for impulse because I use P for momentum, but delta P momentum does equal impulse. So delta P is also technically valid. Delta P equals force times time. All right. 27. A block with momentum P is sliding on a frictionless table and a student uses a force probe to bring it to a stop. In combination with a motion detector, the student plots a force time and force distance graph. which of the following would be an estimate of P? So P is the momentum. As Izagani previously mentioned, the two big things that you can calculate in AP Physics with a graph is either slope or area. Which one would give?
Would it be B? Since the change in momentum is equal to force times change in time, so force time graph.
Cool. So based off of the previous thing, we know that the momentum is equal to the impulse, which is equal to the force times the time. And the area under the curve would be the force times the time. And that would be part B. Answer B. Good job. So I know that I've got momentum, which is equal to impulse, which is equal to force times time, which is the area under the force time graph. 28. Ooh, these are funny dotted lines. A 2-kilogram puck traveling north at 5 meters per second on frictionless ice is given a short 10 Newton second impulse to the east. Which of the following is a possible path taken by the puck? Okay. So I'm moving north. I'm given a slight impulse to the east. So this would be to the north. Oh, to the north. And then the impulse is to the east. Which one is the possible path of the puck?
B.
How do you know it's B?
I remember watching the review video and it said something along the lines of the vectors always stay the same.
Good.
So, and it would kind of be in the middle of that. So it would have to be north and east. So it would have to be in like kind of in the middle of that, the line.
Good. So an object in motion remains in motion until acted upon by an outside force. In this case, the object was going to the north. It should keep going to the north. I've now put a horizontal force on it, so it'll start also going a little bit sideways. So I'm going up and sideways at the same time. That's going to take me off at an angle. I don't really need to know the values of these things, but I know that I'm going north and then east after the impulse. So I can't just change direction entirely, right? I'm not going to stop going north. I'm still traveling north. I'm not going to start going south here. And I can't just jump and then keep going north, because once I hit, I should have both a north and an east component. You could also think about playing in the rolly chairs. You're rolling, somebody pushes you from the side, you keep rolling, but at the angle. Cool. Please stop me and ask questions as things are becoming less clear. 29. A spring-loaded system consisting of 2 equal mass carts is moving to the right at 12 centimeters per second on a frictionless surface when at time equals 0, the spring is released. The front cart travels 32 centimeters from 0 to 2 seconds. So it's going to go that way, 32 centimeters. How far does the back cart travel between t equals 0 to 2 seconds, and in what direction? Woo. All right, anybody got a plan of attack for this one?
Can this be treated as a momentum problem as well?
It can.
Because I was thinking that you could take the momentum of the cards together in the beginning and then
Okay.
take the momentum of the front cart and then try to use that information to find the momentum of the back cart, and that would give you a direction as well, possibly.
Cool. Okay, so I've got initially, this one has a mass of m, this one has a mass of m because they are two equal mass carts. So it would be 2m times v sub 0, and in this case, v sub 0 is 12 centimeters per second. And then afterwards, they have to add together to equal that value, right? So that's going to be m of the front times the velocity of the front plus m of the back plus velocity of the back. So afterwards, from 0 to 2 seconds, it went 32 centimeters. 32 divided by 2 gives me 16 centimeters per second. Okay. So I know that these two masses, the mass of the front and the mass of the back, are equal. So it's just going to be m and m. So this was 2m times 12 equals m times 16 centimeters per second plus m times my unknown velocity. 2m times 12 is 24m equals 16m plus vm.
At this point, wouldn't it also be a good test taking move to just like eliminate half of the options?
Yeah, which half?
The ones moving to the left.
Sure. And how do you know that I can eliminate the ones to the left?
Because it has to add up to 24 and you have 16, so you have to have something positive.
Good. So minus 16 minus 16, 8m equals vm. V has to be equal to 8 centimeters per second, right? Because it's a velocity. And then the question was, how far does the back cart travel between 0 and 2 seconds? And in which direction? And since it's going for 2 seconds at 8 centimeters per second, that's 16 centimeters that it would travel to the right. Anybody attack this one slightly differently? Okay, one other way that I could see going about this one is just like on a conceptual basis. If you have an idea that like the before has to be equal to the after, which it does, right? Before has to be equal to the after. Well, in the 2 seconds before the break, it was going 12 centimeters per second. So 2 times 12 would mean 24 centimeters total. Once they split, I've got to average 24 centimeters. So I know it went forwards 32. 32 plus what gives me an average of 24. 32 plus 16 would give me an average of 24. Because 24 and 24 is 48. 32 and 16 is 48. So if you know that like before has to equal after, because momentum's conserved, take the 2 seconds before, the 2 seconds after, they have to average out to be the same. So if that makes any more sense to you, that's another way that you could conceptually think through. All right, problem number 30. Cart A, mass of m, moving at 4 meters per second, collides elastically with cart B, mass of 3m. After the collision, cart B is moving forwards at 2 meters per second. How fast and in what direction is cart A moving after the collision? say once again, this is, oh, cart A. Okay.
Is it C?
It is C. How do you know?
I made the momentum before and after the collision equal,
Okay.
and I solved for so I put, yeah, I made the momentum of cart A and cart B, add them together and make equal before and after the collision.
Okay. VB. Okay, and you know that cart B is moving forward at 2 meters per second. So you put in 2 meters per second in here for this one. So this was 4m equals mVA plus 3 times 2 is 6m minus 6m minus 6m negative 2m equals mVA. A has to be equal to negative 2. So you could definitely solve it numerically. Good job. That is an accurate way of solving it. Did anybody just see this and see the answers right and have a logical reasoning for why?
Is this related to what Alex was talking about earlier, where for every like action there has to be an opposite and equal reaction? So if one thing is moving forward at 2 meters per second, then it does
Not
that
necessarily.
apply in this situation, or
So the force would be equal on both sides. So there is an equal and opposite force. In this case, it doesn't mean that the velocities have to be equal in both sides, because it'll vary depending on the masses of the other object. Another way that I would think about doing this is, I know that if I have a perfectly elastic collision and I hit a brick wall, then I'm going to bounce back with the exact same speed that I came in at. So since this one was coming in at 4 meters per second, I know it would bounce back, but not at 4 meters per second because I didn't hit a brick wall. I hit something that's more massive, but will still keep moving. So I think it's going to bounce back at less than 4 meters per second. But I do think it's going to bounce back because it's hitting a heavier thing. And if I have a little car hit the big car, the little car bounces off of it. Little person hits the big person, the little person bounces back. So I think it would be not quite 4 meters per second, but greater than 0 meters per second. So that leaves me with 2. Awesome. Cool. No problem. Next one. Same setup. After the collision, B is moving forward at 2 meters per second. What percentage of cart A's original kinetic energy does cart B have after the collision? So now I'm doing a comparison. A's kinetic energy, so this is, again, mass M, mass 3m. What percentage of A's kinetic energy does B now have?
It would be 100% right, since it's an elastic collision, so all kinetic energy is conserved.
All of it is conserved, but A is going to keep some of its own kinetic energy because you just said that A was going to move backwards at 2 meters per second. So A is going to have some of its own kinetic energy. But since I know that afterwards, A is going to go back at 2 meters per second, and B is going to go forwards at 2 meters per second, you might be able to figure it out without actually doing the math.
Since the mass of A is 1/4 of the total mass, then it's got 25% of the total kinetic energy, which means that cart B has 75% of the kinetic energy.
That is correct. Since they have the same velocities, the only thing that's different is their masses. Since B has 3 of the 4 parts of mass, 3/4 of the mass, it'll have 3/4 of the kinetic energy at the end. You could also just do a math part of it. You could say, okay, at the beginning, it was all cart A. So that was M times 4 squared, right? Was at the beginning. At the end, I'm looking at cart B. So that would be 3M times 2 squared. 2 squared is 4 times 3 is 12, or let's say 1/2 times 12, which is 1/2, which is 6. 4 squared, 6M. 4 squared is 16, so that's 8M. 8M to 6M. 6M is 75% of 8M. So you could do it either way. Both ways work. All right. Problem 32. Drawing not to scale, a 2 kilogram block is released from rest 2.5 meters above the ground on a 0.5 meter long ramp where the block experiences a force of friction equal to 10 newtons. What's the block's kinetic energy just before reaching the ground? Whoo! Okay. All right, how would we set this up?
Couldn't you like use the friction to like find the thermal energy and just take that out of the potential energy, maybe?
Good job. So you know that the gravitational potential energy is going to convert to kinetic energy plus some thermal energy, right? Because I'm going to lose the thermal energy due to that force of friction. So kinetic energy is what I'm looking for. So to get kinetic energy by itself, subtract E thermal, U sub G minus E thermal. Now, U sub G is mass times acceleration due to gravity times the change of height minus E thermal, which is the force times the distance, right? The force of friction times the distance that it's applied for. The mass was 2 kilograms times 10 meters per second squared times delta y, which was 2.5 meters total height, 2.5 meters that it fell, minus 10 newtons over the course of 0.5 meters of ramp. So let's see, 2 times 10 is 20, 20 times 2.5 is 50, 50 minus 5 is 45 joules of total energy. So identifying what all the different types of energy are really important for this one. You know that it's going to be gravitational potential to kinetic. And then you also have to identify that there is a force of friction, but only on that ramp part. So I just have to take away the force of friction while it's touching the ramp, which is for half of a meter. All righty. 33. Starting from rest, a frictionless cart is pushed horizontally with a force probe, and the graph of force versus position is shown in the above. During what section was the change in the cart's kinetic energy the greatest? So we're looking for the change in kinetic energy. And I'm given X and I'm given force. Anybody have an answer that stands out to them or a starting point of how you would think about this one?
Well, in my mind, from 20 centimeters to 40 centimeters, it is exerting the greatest force,
Great.
which then means it's got the greatest acceleration during that stretch.
Good.
And that greatest acceleration should mean the greatest change in kinetic energy.
Yep, the acceleration is the change of velocity. And since kinetic energy is 1/2 mv squared, changing the velocity will change the kinetic energy the most. So I agree, you're looking for an acceleration in this case. The highest value is between 20 and 40. So force is directly proportional to acceleration, changing the velocity, changing the kinetic energy. Good job. All right. Ready for the next one? All right. Same graph, same situation. During what 20 centimeter section was the time to travel that section the shortest? And it is a frictionless cart. That part now becomes important.
Would it be 60 to 80 centimeters?
How do you know?
Because that's when the most force has been applied, so that's when the most acceleration, so it has a higher velocity.
Good. So we know that the acceleration, let's see, the force is positive through the entirety of the graph. Positive force, right? So like the force is positive, which means it's going to be accelerating, right? So that means the acceleration is positive. In here, the force is still a positive value. It's positive 12. Down here, the force is still positive. It's positive 3. So it's still accelerating in the same direction, right? Any positive force leads to additional acceleration, more acceleration. So I've accelerated it up and I'm getting faster and faster and faster and faster every time. The faster I go, the less time it'll take to travel the same distance. Force versus, oh yeah, versus position. Okay, that's good. It's not versus time. Good. I was like, if it's versus time, then that's tricky. All of them are 20 seconds, but it's position, so that's good. So that would be the later in the graph, the later distances, it'll be going fastest, so it'll take less time. Excellent. Problem 35. A block with known mass m is hung vertically from a spring with unknown spring force constant and brought to rest. Which of the following measurements, if recorded on its own, would not allow someone to calculate the spring constant with known mass? Okay, I hate these, the which one's wrong questions. Just personal preference. I think they're bad questions. But whatever, it's the type of question that we have. I'll let you read, see if you can find which one wouldn't work. So we need the spring constant. All right, what are we thinking? Part A, would it work?
Yes.
Yes.
I think.
F equals K delta X, you know, force based on mass and gravity. You've got the distance, so now you can find K. Okay. Part B, pull the mass downwards, release, and measure the time it takes to complete one oscillation. Would it work?
Yes.
How do you know?
Because the time to complete one oscillation is the period, and the formula for the period has the spring constant in it.
Yep. Right. 2 pi root mass over K. But you know that the period is related to the mass and the spring constant. Pull the mass downwards, release, and measure the distance between the highest and lowest points of the oscillation. Would it work?
I don't think it would.
I don't think it would either, because it depends on how far you pull it, right? If I pull it super far down, then it would go further up. If I don't pull it so far down, then it wouldn't go as far up. I think that what that is measuring is how hard did you pull it down. So I would say your answer is C. And I also think the answer is C because I know that the period, the time, like these are the same quest, like the same things, right? But this one's about distance, and distance is not related to the spring constant. Every spring will have the same period, but it can have different distances depending on how far you pull it out or in. And I got to be honest, I have no idea what they're describing in part D. I read through it and I don't understand that experiment, but I know C is not right, so I'm good with C. I've decided C is a valid answer. Don't totally understand what D is describing, but I'm still going to go with C. Cool, cool, cool. Great. All right. Another mass spring system. This mass spring system is stretched, released from rest, and undergoes simple harmonic motion with its position time graph shown below. What is the first time after the release that the kinetic energy of the block reaches a minimum? The first time after the release where the kinetic energy reaches a minimum. Who's got it?
Wouldn't it be 5 seconds because kinetic energy is maxed when it's in equilibrium?
Kinetic energy is maxed when it's in equilibrium. And is it at equilibrium at 5 seconds?
Or sorry, I was looking at position. It would be 10 seconds. Sorry. I was looking at the 5 up at the top and not the 5 on the x-axis.
Okay, good. Yeah, so it needs to be at a maximum or a minimum. The other thing that you can think of is this is position versus time. So the slope of position versus time would give you velocity. In this case, the velocity is 0 at the top of the loop or the bottom of the loop, right? So I'm looking for somewhere where the slope is 0, has a velocity of 0 as it shifts directions. It's going from up to down or from down to up. And that would be at 10 seconds, B. And that's the first flat point after the release being at time 0. A mass spring system is stretched, released from rest, and which of the following is equal to the distance from the equilibrium position that the mass was initially stretched? Okay, distance from the equilibrium position, and now it's a velocity versus time graph. Pay close attention to the axes. Okay, so let's look at part A, the peak of the curve at time 2 seconds. Right there, what does the value 2 give you? Does it give you a distance? No, Mr. Williams, it gives you a velocity. That's right. The value 2 listed on the velocity axis is a velocity. The slope of a line, since it's a velocity graph, what does the slope of velocity represent? The slope is the rate of change of velocity.
Acceleration.
That is an acceleration, so that ain't it. Area under the curve between 0 and 2. What would be the area under the curve of velocity? Is that a distance?
Yes.
Yes, it is. Yeah. So this one's really just a review of on a velocity versus time graph. The value gives you the velocity. The slope gives you the acceleration. The area under the velocity curve gives you the distance. So that would give you the total distance under the curve. And then the average value of the curve between time 0 and 2, which just gives you the average velocity, not the instantaneous velocity, just the average one. Okay. All right. 38. We're cruising along here, guys. Good job. We're going to get to 40 and then maybe even some. Problem 38, which of the following would allow for an experimental estimate of the free fall acceleration on a given planet? Choose 2 correct answers. All right, both of the correct answers seem like inefficient ways of doing it, to be perfectly honest, but there are two that are technically correct.
Is one of them C?
One of them is C. How do you know that one of them has to be C?
Because the equation for a pendulum has G in it, so you can solve for that.
That's right. As long as it has G in it, you can solve for it, right? G is the acceleration due to gravity. And the equation for period of a pendulum has G in it. T equals 2 pi root L over G. Which of the other ones would have G in it? Which one would G impact?
The 250 ground mass oscillating vertically.
Oscillating vertically on a spring. Okay, and why would that have G in it?
Since it's going vertically, it should be affected by gravity. Although I can't find an equation that actually includes gravity in it.
Yeah, I agree. There should be a component due to gravity, but because we're measuring the period, that's the thing that we're measuring, and the period of a spring is 2 pi m over k. Mass and spring constant do not include gravity. Now, if we're thinking about the energy there, you could say like, okay, we've got U sub G plus U sub S is converting to kinetic energy there. You get that transfer between gravity. Anyway, but none of these have time. So that one doesn't work. I see A. Okay. I would argue that A, the height that it rebounds to after bouncing, I would say that is a measure of the elasticity of the ball and of the surface of the collision, right? If it's fully elastic, no matter where it happens, it'll bounce back to the same height. If it's not fully elastic, no matter what the acceleration due to gravity is, like I can have it, something on the earth bounces back close to 2 meters height or drops and just sticks to the ground like a little ball of clay. That's really a measure of how elastic is the clay versus a golf ball, right? Golf ball is going to bounce, clay is not going to. So I'd say that's a measure of elasticity, which leaves me with B, time a solid sphere and rolling without slipping down a 1 meter ramp angled at 30 degrees above horizontal. You have so many details in there that make this an inefficient experiment, but it is being pulled down by gravity. So I could find the acceleration due to gravity.
Yeah, that makes sense in my head when I was looking at it, because you can find velocity with, distance over time, and then it's just over time again for acceleration.
Right.
Like the numbers there work.
Yeah. Technically, I think this would be like there's a rotational part because it's rolling without slipping. So you'd need to know the rotational part. You'd need to know you have to use this 30 degrees above horizontal and do some division to figure out which component of it is vertical, but you could get there eventually, okay? Just in an inefficient way. So I'd say B and C. Problem 39. Pictured below is a box at rest on a beam held up by a frictionless pivot on the left and a rope on the right. The box is currently at the center of the beam. If the box were to be moved to the right side of the beam, what would happen to the tension in the rope and the force on the pivot? Okay, so it's here, and I'm going to move it from here out to here. Okay, so now the box is out here. My force is now further out. Okay. So what would happen to the tension in the rope, and what would happen to the force on the pivot?
Would it maybe be C? possibly.
Okay, tension in the rope would increase, but the force on the pivot would decrease.
Just because I think, well, I'm kind of comparing it to how, like, when we were in class and Mia was asking you if you had your hand on the ruler and your finger was closer, there was more tension on your finger when it was closer on your finger versus if you had pulled it out on the meter stick.
Good. So that would be on the pivot, right? Your finger in that case is the pivot. And so you're right. The pivot, the closer the object is to the pivot, the more force there is on the pivot, right? So the closer the object is. In this case, the object's closer to the pivot at the beginning because this is my pivot point. So I think you have the right idea that one has to increase and the other has to oh. Yeah, so you're right. I think. Geez, are you right? I am genuinely confused. I believe.
So this is a torque problem.
It is a torque problem.
So the closer to the, well, wait, never mind.
So I like the concept that one has to increase and the other has to decrease. Because torque has to remain balanced. And the concept of as you move closer, it should change. So 39C, yeah. That is in fact correct. Good job, Jordan. And I honestly have to check the key on this one. I'm pulling up the key and it is correct C. Balancing torques with the axis of rotation at the pivot, the box now applies a greater clockwise torque. So the torque out here, nope, that's J, that's T, torque has increased. So the rope needs to apply a bigger counterclockwise torque to balance. So the rope has to pull up harder. The pivot cannot apply a torque about itself, but now there's a greater upwards force of tension and the downwards forces have not changed. So the upwards force from the pivot decreases. Cool. So the tension increases because I'm closer to the rope. And so more of it is on the rope and less of it is on the pivot. The other thing is you can think of is I'm sharing this between two locations. I'm sharing it between the rope and the pivot point. If I'm taking more of it with the rope, then I'm taking less of it off the pivot. Question on that one? Lovely. Number 40. We can do this. Cruising along. A rod is spinning clockwise around a frictionless pivot when, at a certain moment, two forces of equal magnitude are exerted on the rod, as shown below. Which of the following describes what is happening to the angular speed of the rod about the pivot and the force of the pivot on the rod? Ugh. Goodness gracious, this is phrased tricky. Okay, a rod is spinning clockwise. So step one is I have to remember which direction clockwise is. Clocks go around in a circle like that. That means they're going around like that. Okay, that direction is clockwise. And now two forces of equal magnitude. And this is a top view, so gravity doesn't matter. Okay. Describes what is happening to the angular speed of the rod and the force of the pivot on the rod. So first, I'll just note that this distance, x1, is less than that distance, x2. Okay.
The angular speed would be decreasing, right? Because the torque, there's more torque on the right part of the pivot. So it would be going counterclockwise. So, and that would be decreasing the angular speed.
That is right. Angular speed would be decreasing because, as you mentioned, there is more torque on this side because torque is equal to force times distance. Sorry, force times radius, perpendicular force times radius, and both forces are the same. But this radius is less. What? The one that's closer in should be winning. Okay. Okay, and then the force of the pivot on the rod. Since this is a top view, right? The force of the pivot on the rod should be 0. So the two forces are going to cause a net torque about the pivot, but they will not cause a net force, right? The two forces are here, equal and opposite, but the torques are not equal and opposite because the torque is based off of the radius. So I agree. I think you should be decreasing, and the force on the pivot is 0. Force of the pivot on the rod is 0. Because both forces, neither force is actually exerting on the pivot. They're just exerting on the two sides of the rod. Questions there? Okay. 41. 2 ramps. How are we doing? Okay, we got 5 minutes left. Should we bang through 2 more questions? Finish strong? Go through 42? Cool. I hear it's the answer to life, the universe, and everything. So 2 ramps are set up as shown. The ball rolls without slipping on surfaces 1 and 2, while surface 3 is frictionless. Okay, so this one is no friction. The other ones have friction, so the ball's going to roll. Okay. Which of the following describes the maximum height that the ball will reach on surface 3 if released from rest on surface 1 at height h? Ooh.
I would say C.
Less than h, but greater than 0. Okay, and I agree with you. Why do you think that?
Because energy is still being lost to the coefficient of rolling friction on surfaces 1 and 3. So it's not going to be equal to h, and it can't be greater h due to gravity. So it should be less than h.
Good. I would say that I would agree with your answer. I think we know that it can't be greater than h, right? It's not going to be able to go higher because the initial energy is potential energy and it can't go higher than its starting point. I also know that it won't go 0 because it will go somewhere up that ramp. It's coming down with some velocity, so it should go up the ramp in some way. It will do some rotational kinetic energy and some translational kinetic energy on its way down the ramp. Once it hits here, the translational kinetic energy will still be in action. The rotational kinetic energy will all be lost because it'll just be spinning on a no friction surface. And as it spins around that no friction surface, all the rotational energy doesn't help it go up the ramp, right? It would need to stick to the ramp and use that rotational energy to push itself up the ramp. But it still has the translational energy that would carry it up some of the ramp. So the rotational won't help it, but the translational will. So it will go part way up, but not all the way up. Sound okay? So what I've got basically is gravitational to to K rotational and K translational. And then here I have just the translational part going to U sub G. The rotational is lost because there's no friction on that surface. All right. Last one for us to end strong for today. A solid cylinder rolls without slipping, encounters a ramp and rolls to a maximum height h. If a hollow cylinder with the same mass and initial translational velocity encounters the same ramp while rolling without slipping and doesn't fall off the top, what vertical height will it reach? Okay. So this one is solid, and then the next one would be hollow. Is it going to be equal, greater, or less than? Okay, so I know that it has the same translational velocity, going the same speed coming in.
They would have different moment of inertias, right?
They would have different moments of inertia. That's correct. Okay. Thoughts on this one?
Since all of the mass is going to be towards the outside of the cylinder, since it's hollow, that should give it more rotational inertia.
Good.
And therefore it's going to be rotating stronger, for lack of a better word.
Good.
It's going to be rotating harder, and therefore it should go up more if it rolls without slipping.
Good. So basically, we know that both of them are coming in with translational and rotational kinetic energy. They have the same translational kinetic energy. Those are equal. But the hollow one has greater rotational kinetic energy. All of that energy, because it's going without slipping in any way, all of that is going to get converted into gravitational potential energy. So the first one gets converted to gravitational potential energy, but the second one has more total energy because it has greater rotational kinetic energy because more of the mass is on the outside. Therefore, it has more initial energy. It needs to have more final energy. So more gravitational kinetic energy. It should go higher at the end. It also gives you the helpful hint and doesn't fall off the top, which is a good indication that it probably goes higher. if you're worried about it flying off the top when you weren't worried about the first one flying off the top. Perhaps that's a clue. Cool. But physics-wise, we can say more initial energy leads to more final energy, leads to higher up. All right. So that puts us past our stopping time. Couple reminders. Number one, if you haven't already downloaded the AP testing app, please do so. I'll check in with everybody. And number two, remember to get a 3 is 40% on the AP test. A 4 is like 50 or 60, 55, 60%, and a 5 is like 70%. So even though these questions are hard and they take a while, you know, you want to bang through them, and I think we're in pretty good shape. How we feeling? 1, 2, or 3? 3 is like, I'm feeling like these are kind of making sense. So 1 is like, oh dear. Dos. 3, yeah, buddy. And Alex and Michaela, unknown, but hopefully we're starting to come back together and starting to pick it back up. Awesome. All right.